On to module 11 now, which is buffers, titrations, and polyprotic acids. So we're going to start off with buffers, and to know what a buffer is, we have to understand what the common ion effect, which the common ion effect is essentially a soluble salt. So soluble salt plus a weak acid slash base, which both produce the same ion. So then take, for instance, if we were to take sodium acetate, that's an H, and acetic acid, they would both produce the same ion. As in, if I were to take away this H and this sodium, then we would be left over with the acetate ion, which in this case for acetic acid and sodium acetate is our common ion. And to understand kind of what the common ion does, I'm going to do a little drawing for you guys. So say that we have this container with solution in it, and into the solution we're adding sodium acetate, which sodium acetate is a salt. So like this is our soluble salt, and what salts do, that's too many O's. Okay, well what salts do is that they dissociate completely. So in the solution right now, all we're going to have are sodium ions and acetate ions. Like there's no sodium acetate into it because it fully dissociated into its ions. So then now let's say that into this solution we want to add some acetic acid to it just for fun because that's what we want to do. So then acetic acid is a weak acid, and as we recall, weak acids don't fully dissociate. So you're going to have some acetic acid chilling in the solution. And you're also going to have some acetate ions just floating around in there. Right? So, yeah. And we're also going to have our H pluses floating around in there from our acetate ion, which, like I said, they don't dissociate completely, so there's no full one-to-one in there, so who knows what's happening. But now, essentially what's happening to our pH is that these H pluses, they can attach to whatever CH3COO minus acetate ion that's in there. So if we have our things just attaching to make more of this acetate ion, there's not going to be much hydrogens floating around in solution, which to measure pH, we use the negative log of our hydrogen concentration, right? So if there's not that many hydrogens in concentration because of these other acetate ions floating around, then we're not going to have the pH that we would normally if this common ion wasn't being created by the salt. And that's essentially what it does, is that it kind of changes our buffer because of the ions accepting those hydrogens or OHs that are in solution, depending on if it's an acid or a base in solution, right? So then, because of that, we have something known as a buffer solution or a buffer system, where it's essentially the same thing as before, where it's a soluble salt plus a weak acid slash weak base. Ugh. A weak acid slash base, but in this case, instead of producing the common ion, which it does, like that's why we need it, what it causes is a change in pH. That because of these common ions that we're adding into it, even if we were to add more H pluses to it, you wouldn't really change your pH that much because these extra ions floating around would just come up and collect that H plus that I added just because they would attach again. So because of that, your pH doesn't change much because your H concentration keeps getting lessened by those extra ions floating around. So to solve for buffer solutions, there's something known as the Henderson Hasselbalch equation. So I don't know if I spelled that right, but it's called the Henderson-Hasselbalch equation, and it says that your pH is equal to your pKa plus the log of your concentration of conjugate base all over your concentration of acid. And then just because sometimes we deal with OH, like in bases, where we don't produce any H plus ions, or like we're not dealing with an acid, then in that case it would be your pKb plus the log of your conjugate acid concentration over your base. Right. So I'm going to go ahead and erase this common ion drawing over here because we need this room to kind of do an example of how to solve for a buffer solution. Be gone. Okay. So then to do an example for a buffer, let's say that we have a 0.3 molar solution. Yeah. A 0.3 molar solution of sodium acetate, CH3COO, and a 0.5 molar solution of acetic acid, and the Ka for acetic acid is 1.8 times 10 to the negative 5. What is our pH? So that's a point, my bad. So then the first thing that we would do, like I said before, this is just to show you guys what I mean by they dissociate completely. So it's an arrow pointing in one direction because it won't go back to it. And you end up with your sodium ion and your acetate ion. And you start off with 0.3 molar and none of these being created. That's a molar. So then your change is going to be the 0.3 molar. So that finally you end up with 0 over here and 0.3 molar here and 0.3 molar here. So then that once you do your acetic acid solution, so that means that it's in water, and this is a weak acid, so we do our double arrows because it doesn't fully dissociate into our ions. We have the acetate ion plus our hydronium ion. So we started off with 0.5 molar here. Liquid doesn't matter. We don't have any of this yet. But because of this common ion effect here, we have 0.3 molar here. So we're going to start off with 0.3 molar here. So then, just looking at this, we know that this is our acid and this is our base. So this is our conjugate base and this is our conjugate acid. So we have enough to plug it into our pH formula. So pH is equal to pKa plus the log of conjugate base over acid, well, concentrations. And we know those. This is our acid concentration, this is our conjugate base concentration, and we can find pKa by doing the negative log of our Ka. So then we just plug that in and do negative log of 1.8 times 10 to the negative 5 plus the log of 0.3 over 0.5. So then we get a pH of around 4.52. And yeah, so like I said, when you guys are doing this at home or like plugging it into your calculator, if you get a slightly different number, as long as it's within the margin of error of 4.52, you should be fine. Like it just has to do with rounding, like I've said. So yes, all this is kind of knowing that your salt dissociates fully first, because that's kind of what you already have in solution. And that's what you're going to start off with whatever your common ion produced by the salt and your acid or base is. And then you just plug it into your Henderson-Hasselbalch equation and you get your pH. So let's do another example problem where in this case we're going to be doing it of a base. So yeah, this is getting erased. But as I said in other videos, if I'm erasing things before you finish writing them down, rewind me, pause it, it's cool. So then, now let's say that I want to do a POH problem with a base. So let's say that I have 0.5 molar solution of ammonia and 0.5 molar solution of ammonium chloride. Yeah, the Kb for ammonia is 1.8 times 10 to the negative 5. What is our pH? So then ammonium chloride would be our salt, because we know that ammonia is a weak base, so this has to be a salt, right? Even if you didn't know what a salt is, that's kind of a way to do it. So then we know that our salt would fully dissociate into our ammonium ion and our chloride ion. So then we start off with 0.5, 0, and 0, and in the end we're going to have 0, 0.5, and 0.5 molar. So then when I do my ammonia solution, again double arrows in this case, we have NH4 plus OH minus, and we started off with 0.5 here, water doesn't matter, and then our common ion, we have 0.5 and then 0. So now we know that this is our base and this is our conjugate acid, so we can plug this into our POH formula of Henderson-Hasselbalch, which again, we have an OH, we know it's POH that we're solving for. So then we do our pKb, which is the negative log of 1.8 times 10 to the negative 5, plus the log of our conjugate acid, which is 0.5, over our base, which is also 0.5, so that our pOH is equal to 4.74. So then that's pOH, and we're solving for pH, which again, even if you guys forgot that this was OH, well, pOH that we're solving for, this is starting off as a base, and the pH for anything basic is above 7. This right now is not above 7, it's less than 7, and that's usually acidic. So we know that we have to do something else, which in this case, to find pH, 14 minus whatever we got as our pOH, and that gives us about 9.26 for our pH, and that makes sense because it's above 7. So it's a basic solution. So then I'm going to erase this part now. But let's say if we wanted to build upon the problem that we just did. So let's say that in this buffer solution, we are now adding 0.01 moles of HCl to 100 mils of the buffer solution we just did. So it's the same sodium, ammonium chloride, ammonia solution. So we're still dealing with this. So essentially what's happening is we're going to find the molarity of this HCl, which is just going to be 0.01 moles over 0.1 liters. which should give us 0.1 molar of HCl, which we know with our strong acids that they'll dissociate completely. So you end up with H plus and Cl minus, 0.1, 0, 0. So you end up with 0 here, and 0.1 here, and 0.1 here. So what's happening is that we're adding H pluses, which H pluses mess with our concentration of our acid, right? So if it's still being added to our other solution, so we have our POH formula plus our pKb, which is 4.74, plus the log in the concentration of our conjugate acid, which is 0.5, over our conjugate base, which is 0.5. But now we're adding HCl, which is that we're adding H pluses, which means we're adding to our acid concentration, which is our conjugate acid. And because we're adding to our acid concentration, that means we're going to be subtracting from our basic concentration. Just because when we add to one, we have to subtract to the other to keep the thing balanced at equilibrium, kind of. So then we have POH is equal to 4.74 plus the log of 0.6 over 0.4 with our new concentrations. And if we plug that in, we should get 4.92, something along those lines for our POH. So to find pH, we do 14 minus 4.92, which gives us 9.08 as our new pH. And if you were to compare our pHs from this problem to the one before, we can see that this pH is smaller, which means our solution became more acidic, which makes sense because we're adding an acid to it, right? So you would expect it to become more acidic, but it's not that big of a change in it, which again is because of this buffer effect of the NH4 grabbing onto them and so forth, you know? So yeah, that's pretty much it for the common ion and buffers.